Good afternoon, sirs. Dr. K. Senthilkumaran is currently Assistant Professor in Indian Institute of Information Technology, Design and Manufacturing, Kancheepuram, Chennai. He is also the head of the Center for Smart Manufacturing at IIITDM, Kancheepuram. He obtained his doctorate in additive manufacturing in the Mechanical Engineering Department of IIT Delhi. He previously worked as a guest researcher in the Systems Integration Division of National Institute of Standards and Technology, USA. His research interests are in additive and sustainable manufacturing. He is associate editor of ASTM Journal on Smart and Sustainable Manufacturing. He is a member of ASME, SME, SAE, and IEEE. He is also a member of IFIP WG57 Developing Smart Manufacturing Technologies. He has been nominated for prestigious in residence program for Inspired Teachers at Rashtrapati Bhavan during 2016. He has more than 30 international publications in peer-reviewed journals and conferences. He is also a regular speaker at various design and manufacturing workshops and events on design and manufacturing. He has taught more than 10 courses on design and manufacturing and maintains an online portal called manufacturingportal.in for blended learning in design and manufacturing education. As part of outreach activities, he is also the coordinator for Teaching Learning Center at IITDM Kancheepuram, funded by MHRD India, which develops extremely affordable digital fabrication technologies for colleges, polytechnics, and schools for STEM. He is also in charge of the division for the additive manufacturing lab at IITDM Kancheepuram, funded by MHRD India. I welcome you, sir. Thank you.
Okay, thank you, Mr. S. Dhanashekhar. So today, my topic of interest is, I'll just share my screen. Okay, so hope you are all of you are able to see the screen. The idea of 3D printing or rapid prototyping or the additive manufacturing is to transform the way we conventionally manufacture objects. One of the way that we have been manufacturing objects is through adding layer by layer, um, the parts. So when we are making something, let's say when we try to make something, so we use either heat or we use force or we use sometime pressure to shape and create the object that we want, right? So essentially 3D printing means we are able to produce an object by dividing them into number of layers and then producing each layer at a time, right? So whereas in conventional manufacturing it may be shaping a material through deformation, or it may be creating an object by successively removing layers of material called machining, or sometime changing its phase from solid to liquid and pouring it into a cavity and making it solidify to take the shape of an object. So these are various ways in which we create objects, right? So but today's topic is of more of interest in design. So let me just straight away go to my topic. Yeah, so the first thing that I'm going to talk about is all about enablers and objectives. So what are the enablers for 3D printing, and what is the objective? So 3D printing can create excellent geometric freedom. So it can cope up with the geometric freedom. So people say when you can imagine something, you can make it. So the only limitation for people is imagination. So how was this possible? And also 3D printing is touted as the next industrial, one of the technologies for the next industrial revolution. And what are those technologies? Why do we call 3D printing as the next generation technology or the very progressive technology in manufacturing? So essentially, there are many enablers and there are many what you call as drivers, right? So the drivers of 3D printing, what makes 3D printing so special, and how it is enabled is discussed through a couple of slides, right? So we'll just start with understanding the enablers and the objectives. Now, what are the enablers and what are the objectives, right? So when we look at the enablers, let's say for example, we have personalization or individualization is one of the very important enabler for 3D printing. So we call this as individualization. Means like you are able to customize the geometry for masses, right? So you are not going to provide the same design for everyone. So you are able to customize it for the individual needs, individual taste, individual preference, the color, the texture, the object shapes, however complex it may get. So we would be able to provide them with a personalized object, right? So that is what we call as the enablers and the objectives of 3D printing. So first enabler is nothing but personalization or individualization or customization. So earlier we were constrained by the ability of the design to you know uh, to basically to be produced through an intermediary shape like dies and molds, right? So then we had toolings. So essentially they constituted a huge amount of effort and a sudden change in the design. You might not want to throw away your existing dies and molds, which are very expensive to make. So normally an individual who wants to basically have his own preferred geometry in a color and in a shape that he wants, it would have been not possible through any of the conventional route until he has a craftsman who can do it through carving from wood or from clay or from making it individually in a craftsmanship type of a production, which is not which will be even difficult for any complex objects to be produced, right? So the next is the complexity, right? So what happened over the period is like the complexity has one of the very important enabler of 3D printing. So we had a limitation in terms of the types of geometry that we can be produced in a conventional manufacturing. For example, we cannot entertain undercuts. We cannot have uniform no non-uniform wall thicknesses. We cannot have re-entrant features. Sometimes we cannot even produce in the color we want. We may have to go for a lot of post processing and multiple colors, so you have to only take an workmanship and print it. Textures, you cannot produce textures the way you want, and shape and sizes and complexity. Now the complexity is about it's not just about the geometry, but it's all about material complexity, hierarchical complexity. So you have lots of complexity, right? So let's just look at this particular enabler, which is the complexity. So we need to look at how the complexity of the design could actually kind of create a new value addition for the people who are trying to basically employ these processes, right? So in their manufacturing shops. So conventionally, when we do the manufacturing, the major objective, the major idea of manufacturing using, let's say, conventional machines were limited because of the tool access directions and tool accessibility constraints, and also the constraints in the number of axes that they can control, and the free form surfaces. And having such a complex surfaces is extremely difficult to produce. So the degree of design freedom now is much more than the conventional manufacturing process, just because you are using the divide and conquer principle. Since you are taking a 3D model and then dividing them into number of layers, so you are able to basically achieve what you call as this degree of design freedom by divide and conquer type of principle, because you have taken a 3D model and then you slice them into number of layers. So you converted a very complex 3D object into small, less complex 2D layers. So which you are trying to produce one at a time in the third dimension. So that is how you are able to basically attack the complexity problem. So another important aspect about 3D printing is basically the decentralization. So the decentralization, we just use a laser pointer. So decentralization is more about the ability of the manufacturing processes to be moved closer to where the customer is. So it's not anymore like China is going to be the factory of the world, because we right now manufacture everything in China and then we outsource. Not just we, in the sense the entire world other than China depends on Chinese goods and Chinese manufacturing factories. So they are called the factories of the world, and they make things and then ship it in large volume to the entire continents, right? So now, because of that, we are able to decentralize the production, push the production as close to the customer as possible. You can make it. So that is one very important driver, and it's also an enabler because people are able to make it. And another one is servitization, because today we are talking about servitization from, there is another word. If I say that word, you would understand what it really means, which is also called as the Uberization. So the Uberization or servitization is the ability of the 3D printing processes to basically become servitized, in a cloud type of a manufacturing processes. So we are looking at the manufacturing facilities to manufacture not just for their own use or there for a tier 1 and tier 2 supply, but anybody who can actually kind of use this as a platform as a service. They can use it as a machine as a service, design as a service. So they can servitize this manufacturing equipments and manufacturing methods and processes. So it enables individuals to kind of cut the cost, because they don't have to own a capital intensive equipment. So they could depend upon services of anybody. So you have your own machine, put it into the cloud, people find you through the cloud and marketplaces, then they get your parts fabricated. Second, you can also access machines which may be in your neighborhood, across your street, or in your block, or maybe in your district, or maybe in your town. So you can get connected to this 3D printers through the service discovery from the cloud. So you have somebody puts up a service availability over the cloud through a marketplace like Thingiverse, or let's say Shapeways, or probably any other commercial or even government marketplaces. And then somebody can discover that service very quickly and then utilize it. So it becomes easier for a manufacturing companies, or even for a matter of fact the enthusiasts who have a personal manufacturing capacity in their own backyard, can be connected to the cloud, and then it can be servitized. And now we have 3D printers which can be distributedly operated. People sitting at some place can load the parts and operate and understand how much progress that machine has made. So we have a means by which somebody sitting in some other continent is able to load and create a workflow for a factory that you have in your own backyard. So the distributed nature and the decentralization of the production is one of the biggest enabler for 3D printing. Right. So the fourth one is localization. See, we have been talking about many different aspects of design. Some of the designs that we have, so these designs has not been looked at from a localized angle. Let's say you have a global outlook and global outreach in terms of the market, in terms of the product, in terms of the design. But what exactly happens at this point in time is like when we have a huge demand in the design in the global, but at the same time we need to customize the design to the local needs. This is called as the localization. It's a global localization. So you are going to tend to the market segments across the geographical regions, but at the same time you'll be able to customize the designs to individual needs and individual preferences in those regions, which is called localization. So which is another important driver for 3D printing. And the next important driver is called digitalization. Digitalization is all about the ability of your designs. So digitalization is the ability of your design to eliminate an intermediary shape or an object, something like, let's say, a die or a mold. So your entire manufacturing process operates on a digital thread. So the thread connects all the entities together, from your conceptual design to embodiment design to your inspection, testing, packaging, use, recycling. So your entire life cycle runs on a digital thread. So the digital thread is able to basically digitalize the entire supply chain, your entire enterprise, as well as the life cycle of the product. so that you will be able to use only one single representation of a product throughout your entire journey. So 3D printing takes the digital input and produces the output like qualification reports and everything in digital. So it's all digital. Nothing, you don't need to have a die or a mold or an intermediate turret or copying lathe type of thing. So your all conventional manufacturing process requires a template like a pattern or maybe a mold to reproduce the shape, but here you have everything in digital shape. So the entire digital end-to-end streamlined processes or workflows are available in 3D printing. That is one of the very important drivers for 3D printing, right? So now, so the next important aspect is simplification. So this is about the product. So we have seen the products at the first level as the enabler. Simplified manufacturing processes. So there are not much things that you need to do. Let's say, for example, you have a primary processes and then take the raw material and then take it to the secondary processes and then tertiary process, then finishing, then coating, then painting. So you can actually kind of, make sure that your entire process chains gets kind of combined together in one particular process. So that simplified process chain is another important aspect. Another one is production on demand, which is called servitization, is another important aspect. And time compression, which is called the life cycle. So we have faster product development. The ability for you to make a product much faster is a very important objective of 3D printing. So it is a time compression technology. That's why the word rapid is there. The notion of rapidity comes from three important aspects. One is it's not the process that is faster, but it eliminates a lot of intermediary steps like making a die, making a mold. It also eliminates intermediate steps like process planning. So you can do process planning much faster than a conventional machining or a forming. And also a lot of trial and errors can be done in a virtual world before you can actually make your part, the first part. So this is typically the faster product development enabler, right? So that's is one of the very important enabler. And decentralized production. And then if you look at the product level, it is also reducing the component mass, the light weighting, and functionalization. What we call as, these are all functionalization, E13 to E16. These are all functionalization. Functionalization is adding functional to the existing design. So you take a surface, you add a little bit of texture and add a function. You take a little design and then combine two parts and then combine the function. So integrating multiple functions into one single part through part consolidation is one of the important enablers for 3D printing, right? So the functionalization enables people to basically look at the design from a completely different perspective. So earlier, people, when they started designing, the designers, when they were designing components, so one of the major constraints that they had is about how to manufacture that without any defects, to a record constraints that are there, like the tolerance constraints, time constraints, cost constraints. So now, because of the increased functionality, so you are able to cut the cost, get the product in time to the market, and also you are able to basically customize the needs for the individual customers. So, and this has become one of the very important enabler, because you can combine multiple functions into one single part. Maybe a heat transfer function, a lubrication function, a flame retardance function, a acoustic function, probably a energy storage function, your let's say your like batteries, right? So like you have a energy harvesting function, probably like your RF circuits, which harvest the energy from nearest RF source, or it could be photovoltaic cells which harvest the energy from the sun. So everything, right? So everything can be kind of put into one particular design, and then they could be together manufactured in an additive manufacturing process. So this has essentially resulted in something called as a functionalization, right? So these are the enablers and these are the objectives of 3D printing, right? So now, what are the end objectives? The objective for doing all these things is to increase the performance of the part, to increase the lifetime or durability, or increase the sustainability of the part, and also make sure the maintenance and other things are done easily. The manufacturing lead time gets reduced, the development cost, logistic cost, right? So your sustainability and emissions comes down, and then the company's brand image increases, and then they are able to produce a lot of new business cases, because it opened up an opportunity of new businesses, right? So that is the development of new business models. So the evolution of the new business models through digitalization has enabled everyone to start their own enterprise in no time, because they were able to push the designs to the processes much easier and earlier than what the conventional process were able to do. So this is about all the enablers and objectives of 3D printing. Now, what are the design opportunities? So let's say the opportunities available in design are normally evaluated through multiple means of complexities. So we have so much of design complexities that could be exploited to make sure that whatever you fabricate comes from a beautiful set of tools that can actually take an existing design and then convert that into a very complex design, right? So now why so normally people thought that making a simplistic design works. So we always use the principle called KISS principle. We say keep it simple stupid, right? So but Albert Einstein himself told that the design that works is the simplest one. But sometimes you have additional benefits when you increase the complexity, because unless otherwise specified, when you have a conventional manufacturing process, when you are making something, it creates very high cost when you increase the complexity, because the cost versus complexity curve skyrockets and the complexity increases much higher. So in order to reduce such dependence on the complexity over the cost, additive manufacturing is brought in as one of the best solutions for this, right? So let's just look at this particular chart, which gives you an idea about the complexity versus cost. So this is the cost and this is the complexity. And you can see that the conventional manufacturing, as shown in the green one, so which actually kind of increases over the complexity. So the cost kinds of goes up and goes up as the complexity increases beyond a particular point. So now it becomes a little bit an asymptotic there at this particular point. Now the design for additive manufacturing, because it has lowered the cost, so the cost remains almost nearly same for any increased amounts of complexity with the design or the geometry or the part. So this has paved way. So geometric complexity has paved way for increased margins and increased profits, but the cost remains the same because you are able to add value to the customer's preferences. So now let's see this particular chart, which is given by Professor Guha Manogaran. So here we are talking about three different axes. Let's say we have the volumes and varieties, right? So in the y-axis, and here if you see the complexity here, the z-axis is variety. So the complexity can be very high, the volume can be very high, and the variety can be very high. That is what we call as the complete manufacturing freedom. So I call this as a design freedom, because it's a manufacturing freedom translates into designer's mind. When somebody is not constrained to think for a specific manufacturing process and what not he cannot think of, so he can think of extremely complex objects to produce. Let's just look at this a few technologies and tools in design for additive manufacturing that comes to the rescue of the designers, right? So part consolidation is, as I already told, it's the ability of the designers to combine multiple parts, to combine functions, not just to combine functions, to cut down the assembly cost. Because when you are doing an assembly, so let's say you are sorting and then kind of orienting and then placing, so it takes a lot of time to do a lot of assembly. Sometimes if you can avoid this assembly altogether, your cost can come down. So cutting down the assembly cost, adding more functionality to the part, and then making the part more organic in nature and having more free forms, which could be very easily manufactured rather than simple sheet metals that could be bent and rolled, then formed and drawn, right? So or extruded, all those things. So we don't need to do all those sorts of things. So we don't have to think in a manufacturing constraint, but we can see as a manufacturing as an opportunity for the designers to create more shapes. So you can see this one becomes this and this one becomes this. So you are able to basically increase the complexity. And personalization, as I said in the drivers, it's about mass customization, right? So we are able to customize the parts for a very large masses. So hundreds and thousands of parts can have different designs and still could be manufactured at the same cost without increasing the cost. So this is the more important objective of the 3D printing. So one of the realization that people had at one point in time is that when you have very large varieties of design, so 3D printing is the only way you can make them very easily, because the mold is going to be costly. When you are making a plastic pot like this, like the hearing aid canals in the hearing aids. So you're going to basically consume huge amounts of money in making the molds, or maybe you are going to be it's going to be a little expensive. So but here it's going to be a little easier because you can take 100 designs and nest them in a build platform and print everything together. So that makes this process much more easier for people to use it, right? So now let's just look at this from a distance. This process makes multiple designs, it's like it's a niche product. Let's say for example somebody wants to drill a hole, and then this geometry of the surgical guide is unique to that particular person. To make only one of design, it's not a standardized design that fits for everyone, but it's a one of design that fits for only one person, which is called personalized or individualized or customized part. So the process chain allows to basically do this at much lower cost compared to the conventional process. So this enabled what we call as a revolution, the fourth industrial revolution. That why it's 3D printing is part of it. So you can also use a lot of foam structures, right? So the porous structures, the foams, the lattices. So you can imagine any complex internal structure and you can put it inside the 3D models. So to do variety of things, for example, one of the things that people want to cut down is the emissions, right? So the fuel efficiency is directly dependent on the weight, the curb weight of the vehicles. It could be airborne or land or sea. So the efficiency of the vehicle improves and the weight comes down. So the light weighting or the weight reduction techniques are there. So you could use a foam or a lattice structure or a porous structure. So these structures actually removes materials from the layout, material layout, and then makes it more stiff. It doesn't lose the strength, but at the same time it actually increases the stiffness, that is strength to weight ratio. So these kind of things is possible. So people can take a conventional foam making technique and make a single object, and then they can actually take this object convert them to 3D CAD model through reverse engineering. So the so-called 3D scanning, which is an ecosystem of technology with 3D printing. And then the 3D scanned object can be redesigned, or it can be, for example here, you use a reticular mesh here. So you use the marrow regions of the bone. Let's say you want to try to mimic a bone structure. You can have a low density structure at the interior and high dense structure at the exterior. So the pore volume changes extremely um, uh, rapid, or it could be at one single point. It could be a gradiently, it can be changed. So you can design the way you want and make these forms. So you can realize these forms. The one that you see on the right side is titanium, the lattice structures which are produced using electron beam melting processes, right? So, and you can also use topology optimization. So the topology optimization is a technique where you can take material from unwanted regions in the design. So your design can be lightweighted by having a design which looks more natural, which looks more organic, right? So nature always try to minimize the energy. So the way the rivers flow, the way the trees grow, the leaves spread out. So they all looks at the minimum energy principle. So energy is always minimized in everything what nature does. So let's say we use the same thing. So let's say we try to basically pose an optimization problem in which we want to minimize the compliance of the design by eliminating the unwanted material from different regions of the part. So how do we do that? So one of the ways that we do is to find the material layout, the initial material layout, and define the loads. And able when the loads are defined, let's say for example here, so you take an hydraulic manifold like this, and then you subject it to topology optimization and then eliminate the unwanted material, and then structurally you just see whether the strength is good and optimized, it's fine, and then you can finally make this part. So the way you do this is like you first remove the machined cavities, and then whatever existing material volume you just give as an input, and then find out the stress flows. Wherever the stress flows on the material, keep the material there. In other regions where there is no stress flow, just remove those materials. So it's a very simple technique, but it's very complex implementation. But it enables you to basically identify the regions where there is no material requirement, and then remove the material to make it lightweighter. So you can see here, so a structure like this which has been made to machine, now to 3D print you can make it like this. So you start from here, right? And then you do the topology optimization, then the material gets removed. So you only give the preserved geometry. So you have given this particular geometry as preserved, and this wherever it is, assembled together. So you keep that as here you have assembled together. You just keep this as you know a preserved geometry where you want to basically keep the geometry as it is, and remaining material layout you allow the algorithm, the computational topology algorithm. So there are many methods to do it. One of the most famous method is SIMP, which is called solid isotropic material penalization, which you can use it, right? So you can use many of such techniques, right? Now, so what is happening here is like when you take such a material and then you put the material through the algorithm, then it actually identifies the stress flows and then keeps the material there and removes the material from other places. Then you again subject them to loads and see whether it is functionally satisfying the criteria. So then the structural analysis reveals certain regions where there's a stress concentration. Maybe you can manually modify those, tweak those design a bit, and then you can combine them to form this. So it's like, you start from here and then you go here, and then you do the optimization, and finally you get the component, and then you can manufacture it. So let me just okay. So this is the steps, the various steps that are involved in 3D printing, right? So now let's just see. So this is like a sketch or an implant. So let's say it's a sketch. So you have a 3D model. It has got a lot of holes there because these holes are normally provided for weight saving. So they would have machined out some region. So now we are going to optimize it. So just put the material back and then once for all optimize it using topology. So you put the material back and then you kind of defeature it. Defeaturing means you are able to basically identify the materials where you need to basically have an assembly. So, and removing those machined holes and then keeping the complete material there, and then you define the fasteners and joints and contacts, and then assign the materials and loads, and then generate an ideal shape. So you have created an ideal shape, and then you can use polynubs to fit a very nice smooth surface around it, and then you can verify the performance and then manufacture it. Further weight reduction is even possible by having more lattice structure. So you can put a stud based lattice or a surface based lattice. So there are 50 60 different types of lattice that are available. So you can imagine any lattice you can put it. So if you can design your own lattice structures and then you can put it. So this is typically the final components that you would have designs which are topologically optimized, but also you can further do the weight reduction by adding more structures in it. So, and generative design is an advancement over what you call as this topology optimization. So in as opposed to topology optimization, here we are not defining any initial material layout, but we are only defining a negative volume, which is called the preserved volume, where I don't want any topology optimization algorithm to be implemented. So let's say this particular example here, which is a GE engine bracket, which is the widely studied case study and presented case study on topology optimization. So we have different kinds of loading conditions. We have a static vertical loading, static horizontal loading, and then static loading at an oblique angle, and then we have a torsional load. So all the four different loading conditions are given as an input. And then we also define certain features which are to be preserved. So these are the negatives. So these are the features which I need to preserve. I don't want any material to be there. So those regions are where I don't want to need any material. So here I have not defined any initial material layout. I didn't start with my first design that I had, the original design that I had, the existing design that I had, but I actually told them, so you don't put material, but you give me any number of options by which you can actually solve this problem. So then it gives us, multiple solutions. So the generative design can give you hundreds and thousands of solutions. So thereby you are able to basically evaluate these designs at your own convenience. And then you can say, let's say I want a design which has the minimum support structures so that I could actually make them very easily. Probably then I would like to have some more features, D features being done on it. So it gives me an opportunity for me to kind of look at alternate designs that are available. So it throws open a huge opportunity for people to understand and see the similar designs and then dissimilar designs, segregate them, identify opportunities in each of these opportunities, and then find out one design which suits them. So people can do even artificial intelligence, so kind of reverse through these designs and find out the one. So you can build your own decision support system, any decision logic or decision support system which is designed to take care of kind of part selection based on the topology optimized output or generative design output is the basic idea of many research articles that are recently started coming up, right? So we have also published a paper recently on AI based technique to kind of understand the similarity of the designs, and then looking at from multiple angles, like how a human see the object and observe its complexity by looking at it. So we also designed an algorithm, an artificial intelligence algorithm to do it. So these are things that are possible. Okay, so the generative design outcomes may look extremely similar. So it may be deceptively similar, but it may have some strengths and some weaknesses. So you need a decision support system, an evaluation system to understand these designs, and also to generate these concepts, not just through your stress flow. Sometimes you can also do conceptual designs based on many different aspects. So today I showed a structural example of some structural loads. You can also put heat transfer loads, you can put some acoustic loads, you can put some, let's say, electromagnetic loads. You can also solve problems of any nature or combine physics of multiple nature, or you can have a multi-physics objective function to solve and then optimize the design around it. So it throws open a huge opportunity for people to integrate functions and also optimize the functions using your topology optimization. Let's say I want to solve a problem of higher heat transfer. Let's say I wanted to solve a higher problem of heat transfer by posing a heat conductivity heat transfer problem into the design. So I would be able to find out, let's say, where the heat is flowing. Then I keep the material there, I remove the material where the heat is not flowing. So probably then I add an additional constraint, not just to my structural problem, but it's also a heat transfer problem. I can optimize the fluid flow, I can optimize the heat transfer, I can optimize even my acoustic, I can optimize my energy transfer, I can optimize my flame retardance, I can optimize whatever functional that you can imagine. So you can, if you can form an objective function, you can, if you can formulate your partial differential equations for your problem, let's say whatever functional problem that you're trying to solve, which could be easily solved by any one of the numerical methods, maybe a finite element method or a finite difference, or maybe a boundary volume, or probably computational fluid dynamics. So you can solve the problem and then optimize the geometry around that particular problem. Okay, so this is about the heterogeneous objects, right? So here we are talking about designing multi-materials and gradient structures to take advantage of the possible complexity in AM. Okay, so what are we talking here? So let's say we have the capability here. Today we have the capability here to take a bamboo culp. Let's say you just take a bamboo culp. So it has got graded properties. Look at the fiber content. It varies over the position. So you have a fiber content which varies over the position. So you start from, let's say, one end of the spectrum, that is at the end of the one edge of the object, and then the property varies through the section. So this we can see in bones. In the marrow regions, you have a lower density. In the edges, you have higher density. So you kind of come up with, let's say, a part which has a variation in property. So this kind of a multi-material and gradient structures are, you know, becoming more and more increasingly useful in today's applications. So let it be aerospace, let it be defense space. So you would be able to identify these structures and use these structures in multiple places, right? So now let's just look at this particular example. Like you have a metal, we have a functionally gradient material and a ceramic structure. So now you can see that the metal and the ceramic are merged together not by a distinct boundary but in a graded boundary. So meaning that you are able to combine material properties at a gradient structure, as a gradient structure. So you can achieve multiple types of such a gradients. It's not just material properties but also composition. So you have a compositional heterogeneity that you can create, and you can create property heterogeneity. You can also create structural heterogeneity. So you can create many porous structures. The porosity can change from one point to the other point. So a material is considered to be anisotropic. The property varies over direction. Normally, if you see the 3D printing objects. They are typically anisotropic, meaning that when I take an object, when I try to build them one by one in a one particular sequence of layers, the direction in which I am trying to build will always have a poor strength. So the poor strength arises from the fact that when I'm trying to build an object layer by layer, so what happens is that I am trying to basically kind of stitch one layer to the other layer by kind of locally gluing or melting or solidifying liquid. So this makes the strength in the direction of layering to be extremely poor compared to the other strength in the longitudinal latitudinal direction. So the build direction is always going to be a variation in property is going to be there. So this effect is usually called as anisotropy. Whereas you can also have heterogeneity. So anisotropy is not a desired property. In sometimes in composites, you can see that the fiber directions you will have higher strength, which is a required property. So you want to design or architecture a material to create such a heterogeneity for some functional requirements. It is possible that in many cases you want to design your object, architect your object in such a way that you want to input certain amount of microstructure, certain amount of, let's say, property, certain amount of function, certain amount of behavior in particular regions of the part. So you don't want that entire object to be homogeneous in nature. So by design, right, so by choice, by your wish, right, so by your design itself, you can have a gradient structure, you can have, let's say, a compositionally heterogeneous structure, you can have a property heterogeneous structure. So these processes that we use, like direct energy deposition, powder bed fusion, and then the binder jetting, you could be able to basically tailor these properties, architect these properties, design the materials to produce such an effect. So this is normally not possible in conventional processes. So how do we do that? So let's say you want to build something like, let's say, a compositional heterogeneous object. So what I want to do is I want to create, my, let's say, property to be varying from the center of the object to the edge of the object. So for that, I need to first create a medial axis transform, which is this particular curve for the outside geometry, and then define the guide curves or the rail curves from the medial axis to the periphery of the object. So here you see that these are the two, M1 and M2 are parameterized. So the parameterization has happened 0 to 1, 0 to 1. So 0 means one material, 1 means another material. So here I have both 0, 1, 0, 0, 1. That means, let's assume that you are trying to look at a copper nickel type of a system. So I want copper at one point and nickel at another point. So my 1 means I have 100% copper. 0 means I have 0% copper, right? So then if in this axis, if 1 means M2, this is material 1 and this is material 2. The blue is the material 1, which is, let's say, copper, and M2 is the, let's say, nickel. So I want nickel to be, let's say, 0 at this point and 1 at the edges. So I can define my material parameterized material composition like that. So I can vary the composition over the curve. So wherever, so this is the material composition function. So it's a polynomial function. It could be an exponential function or any other function which could be defined on the rail curves, so that I can vary the process parameters and properties, or sometimes I can actually make the flow rates to be a little changing, or the mass flow rate of the materials to be changing. You can control the composition by tailoring the composition at individual points along the rate curve. So because I have this parameterized value, so I just iterate from 0 to 1. 0 means one material, 0.5 means 50% copper and 50% nickel. So I can just do the parameterized compositional heterogeneity. So this looks like this. So now you can see that all the green is one material, all the blue is another material, but then I also have a green plus blue region, which is graded. So the next important thing is hierarchical complexity. So where we can produce a hierarchical structure. So here we are trying to design structures which repeats in multiple scales, in macro, meso, and nano scales, so that we can get superior properties. So it's like you have, this is the macro scale and meso scale, and then the micro scale and the nano scale. You can see like the same structure. So it just gets repeated in multiple scales. such structures are possible to be produced in 3D printing. So as I said, the copper nickel type of system, you can see that at the edges you can have one nickel to be 100%, at the center you can have copper to be 100%, and then the composition gradually changing over its radius. So such a type of graded material properties or a full color properties or different materials to be combined in ways it's not possible before. So this type of multi-material structures can possess lots of smart functions. So it can have multiple functions or multiple visual feedbacks or visual clues, or it could be used to represent architectures, real world objects like cartography, or topography, or sometimes even town planning structures. So all those things, remote sensed objects and things like that. So even your FEM results of an object, cutaway section of FEMU could be 3D printed and then showcased. So your multiple color, multiple texture, and multiple material structures could be possible. That is what is we call as material complexity. So the finally, it's a more important thing is the functional complexity. So the functional complexity leads to many different types of functional enhancement to the design. So the first thing that we talk about is multifunctional. So structural, thermal, and fluid. So you can have structural function, thermal function, the fluid functions integrated into one. So normally what people do is like they provide separate cooling functions by running the pipes or drilling a hole. So you can drill straight holes. Along these holes, the liquid will flow and the cooling will happen. But normally, what happens is like in order to increase the effectiveness of this, so you can actually have conformal cooling channels, which actually takes the shape of the surface that you want to cool. So thereby increasing the performance enhancement. So you can also do electronic functional integrations, like let's say you have a forged part or a cast part. Then probably people were doing a lot of weight savings by carving out parts through machining. But right now, instead of that, you can actually kind of optimize the structures by putting lattice structures, hierarchical structures, porous structures, foams, topologically optimized structures, and then also combine your antennas for IoT applications, and your batteries, and you can pattern your batteries, your then inter buses, interconnects, and then your photovoltaic cells and RF energy harvesting antennas. So your active devices, passive devices, they can be combined. So you can combine the electronics functions, energy storage functions, and then mechanical functions, and then also your other functions such as lubrication and then smart functions. They all can be combined together to produce this very beautiful functional integrated part. So this gives you an idea of overall summary of whatever I discussed about the design opportunities. So here with this slide, we end the design opportunities portion of it. So if you look at the design opportunities, we have the form complexity, where we have the hierarchical complexity, we have the functional complexity, and then we have the material complexity, which adds to all this what we call as the enablers versus objectives. So the objective is to basically have reduction in design space, improvement in flow dynamics, improvement in damping, improvement in energy conversion efficiency, improvement in energy absorption. You have design improvement in designs and aesthetics, and then weight reductions and ergonomics. So you have varieties of such improvements that are possible. In the same way, it also leads to a lot of cost reduction. So the cost reduction in assembly, material, and then quality assurance, logistics cost reductions, and then developmental cost reductions. And also you have improvements in sustainability. So sustainability is all about reducing your energy footprint, material footprint, water footprint, and cutting down the emissions on air, water, and land. So essentially, we are talking about, we are assuring that the materials that we use are safe, very less and very efficient. At the same time, the cost involved in developing the material and inspecting it and then doing logistics and everything gets lowered, right? So these are some of the improvements. Now, finally, the title of my lecture was, the confluence of art and science. Earlier, we were talking about form meets the functional and function meets the form kind of a design, where we were thinking about form, certain form, how it should be produced. So people who had the excellent creativity, who have their brains, especially some portion of their brains are very creative. I think you know which portion of the brain, right? So they use that. But usually we say that, in our culture, that we have two parts of the brain. One part of the brain is for the thinking and creatively, and another part is for the thinking mathematically, or what you call as thinking for a normal day-to-day activities. So the creative brain, right, so and also the calculative brain, both can work together in artificial intelligence type of a system. So the artificial intelligence and 3D printing uses something like a generative adversarial networks. So we'll show what it is and then how it can be done. So this is how normally, workflow for a design for additive manufacturing will look like. So you have functional and economic requirements here, and then check the suitability of AM, and then you have the classic design production processes, and then you found an opportunity here. So there's a design opportunity which I highlighted in the previous slides. So once the opportunity is found, then design an AM process chain, and then also the materials that should be used in this process, and then what are the methods to basically link that requirements of the properties to the materials, right? So that matchmaking is done here, and then the initial cost benefit analysis is being done here and the cost calculation methods, and then it proved to be economical. Then you go to the classical design production process. If it's not economical, go back to the classical process. If it is economical, then come to this macro level: topology optimization, generative design, lattice structures, right? So here you have you have all sorts of this particular aspects. Here you can see this. You have defining the lightweight structures, surface modified products, internal geometry for the functional prototypes. You have all these sorts of things. So you can design all this macro level, at micro level, multi materials, material gradients, AM assemblies, everything you can do. Then you can use the geometry optimization, and the product realization chain can continue. Now, so what is the deep generative design framework, which is combining the art and science part together? So, because design is usually an artist with, you have an industrial designer who has a studio called design studio, where he sits and then sketches the parts, sketches the new car design, new airplane, how it should look like. So the human mind is so creative. But now we are using artificial intelligence to bring that human design mind. So that's why we say the confluence of art and science. So you gather previous designs around the same object. Let's say you are designing a motorbike, you are designing an aircraft, or you are designing a hovercraft, or any shape that you want to design. So what you do is you gather your previous designs, right? So then generate new designs by topology optimization, and we use a filtering technique. So we use the filtering techniques, filter the similar designs, see how much percentage of new designs, what is the fraction of percentage change. Then you train with generative adversarial networks. So then filter the similar designs and take the designs which are farther apart from the generated design outcome, and then kind of use the encoder to visualize the design attributes by attributes, create a dashboard, and then you can actually create a deep learning network to kind of understand the design and its variations and the endpoint objectives that you have listed. How much material gets saved, how much assembly cost reduced, how much savings in, let's say, your functional other aspects like energy and impact and heat transfer. So how these things, so you can identify all those opportunities and based on your objectives, and go to the enabler, right? So that is a deep learning network to kind of iterate this process again, and then you give the training data and test data and reference designs. You can do it. So the principle here is like, you have a, let's say here, this is an example of an aircraft design. So these are very simple examples, but there are very complex examples which are available. So we take an input point cloud of an aircraft. So how roughly an aircraft should look like. So this is the initial data that is to be given to the network. So this is what we call as input point. Then we have the matrix representation of the input point cloud, and then you transform the inputs, and then we have the shared model. So we have a multi machine learning techniques for each of these problems that we have defined, and then we have concatenate. So then you can say, like, we have 1024D feature vector that captures all the geometric information of the input point cloud, and then you can classify using the true or fake classifier. So because this generative adversarial interest comes from the image, right? So when you want to basically identify the deep fake image, so they use the generative adversarial network. So we use the same network there to kind of train to understand the design features present in a point cloud and use it for the iteration. So in the generative network, once the latent variable is obtained, you use the generator, and then you train it with the generated data, and then create a mesh and use the discriminator where it gives the wings, tails, right? So it gives the nose, and it gives the engine part. So you can identify them by the classifiers, and then you can create a mesh for a new design. So you can see that the initial data, the data that has been created is like, there could be a jet plane and fighter aircraft, transport airplane, swept wing, bomber, straight wing, propeller plane. So these many designs have been collected. So there are almost 7,000 8,000 designs that are input as a training data. And then the interpolation, then you can see that all these different planes data is given as an input, and finally you get an output, so which is typically, you get a so performance score of all the generated output. So the shapes, the individual forms and shapes that can be created with this type of a data, finally you can train the network actually looks at the features, and then it may give a some kind of a false positive initially when you have very small amount of drag coefficient. So you can also add functional requirements like the drag coefficient. So you can train for individual constraints like how much drag coefficient you want on the aircraft and things like that. So you can get that design done. So coming back to the original design, so you have seen how it is normally done. Like you can take a topological design and then use the generative adversarial network to train for an existing shape and identify an alternate design. And then these designs can be hugely creatively done by artificial intelligence techniques. And then the network will create an excellent industrial designs or freeform designs, which could be then taken into further designing. So this is just an example, like that we can design for many such examples. So thank you. This is a deep generative framework that we discussed, right? So thanks for the opportunity. I think the 1 hour time, I think I just kept the time. So time for any questions, so I'll be able to answer. So if there are any questions, please, you can ask the questions now. So I must be able to answer some of the questions that you have. So let's say you want to have a design that meets the, let's say, the standards of conventional design. So you need to have more number of input data points for the network to train, and you also need additional feature vector definitions and variables that you can use. So the generative adversarial networks can be used to kind of create a generative design outcomes, which would otherwise be normally taken from an initial design space and then use topological optimization. So it's as opposed to using a topological optimization, you can also use generative adversarial networks to create such forms. So this is form follows the function. So this is like function following the form. Okay, so it's alternate to that. That's how the generative design is usually projected. Okay, I think thank you all for your patient listening. So if there are no questions, I hand over the session to the organizers. Okay, thank you.
Good afternoon to one and all gather on this wonderful session. I would like to present the vote of thanks. Initially, we take this golden opportunity to thank our respected chief guest of this session, Dr. Senthilkumaran sir, in 5 days workshop on research scope in additive manufacturing for his august presence and sharing valuable and informative things in additional manufacturing system in his very busy schedule. I extend my gratitude to respected our management principal and our beloved HOD, Mr. Danny sir, for continuously supporting us to conduct this type of online workshop events from mechanical department. I also would like to extend my sincere thanks to Mr. Dr. Seville sir for continuously organizing this type of online or offline workshop on behalf of the mechanical department. I want to thanks to Mr. Anandaraman sir, who is continuously working behind this type of online events. Finally, I want to express my heartfelt thanks to all participation and faculties for the enthusiastically participate in such a wonderful workshop with your patient. Once again, I thank you all, sir. Thank you, sir.
Okay, thank you. Thank you for the opportunity, and thank you all. So goodbye.